All right, so we're looking at a question about spectra. Okay, you can actually find it in both module 7 and module 8, but we're trying to look at this in terms of the context of module 7. Okay, so this is from the 2020 Independent Physics paper, question 35. It says, explain in terms of physics principles or models physics involved and what diagram aims to communicate. So let's kind of look at this. This is obviously some type of spectra. So what the diagram is trying to show us is a emission spectra. Okay, that's the model we're trying to deal with here. So let's put that down. So there's that. What else are we trying to show? We are trying to show that we have these electron shells. And we know that according to the Bohr model, and also the way emission spectra are formed, that each energy level has a distinct, or each electron shell has a distinct level. So here we have, this is an entire atom, the whole thing here, that's an entire atom, and these are the electron shells. So we're saying the model, what the model is trying to show us is in the atom, each electron shell has a discrete energy value. Okay, that's what is being shown to us. And then what other things are we seeing? So the model is showing this. The diagram depicts emission spectra formation. So it's trying to show us how an emission spectra is formed. We have violet light here. We have sort of a blue-green tinge. Let's just use this color to highlight that. And then we have red light forming over here. So that's what we have all together. Okay, so what can we say? So in order to form an emission spectra, the electrons from a high energy state, high energy shell, will transition to a low energy shell by releasing electromagnetic radiation. In this form, it is visible light. So we'll transfer to a low energy shell by releasing more energy equivalent to the energy gap. Okay, so that's how we get the release of energy. And what we know is the energy that we release will be equal to Planck's equation. Okay, so there's that. What else is this diagram showing? Well, this diagram shows that for the violet light, it goes from a transition of 5 to 2, and that has a low wavelength. For red light, it has a transition from 3 to 2, and it has a high wavelength. Now we know that a high wavelength equals to low energy, so that's another thing we can say, okay? So it also shows the higher transition. We use, for example, that N5 to N2 will emit electromagnetic radiation with a higher energy. And how can we say that? So according to Planck's equation, if we put wavelength into the equation, it's Planck's constant over the speed of light over lambda. Okay, so if we have a high wavelength, as you see here, then E would be small. If wavelengths are small, then obviously energy is higher. So we'll emit an EMR with a high energy compared to the transition of N3 to N2. So that's essentially what the diagram tells us. As you can see, we have gone through the model. The model is showing the discrete energy levels. We've talked about the formation of electromagnetic radiation, and we also specified why is it that specific color. The reason why it's the specific color is because the energy we're looking at is the final level minus the initial level. So that gives us an idea of where everything is, all the difference between the two. We also looked at how this relates to wavelength. So we can see that this has a higher energy, and on this side we have a lower energy. And so that's kind of what we're saying here all together, because if you have a low wavelength, that's due to a bigger transition or bigger energy gap transition in comparison to a larger wavelength there. So that's how you do the question. If you're not sure, replay it again and catch you later.